Hello everyone, my name is Eugene and today I'll be talking about geometric algorithm for finding primes with parallelization. First, let me ask you a question. Have you ever watched a movie, The Imitation Game? It is a movie in 2015. It's about Alan Turing, a British mathematician and computer scientist, trying to break a code enigma being used by Germans during World War II. So what made enigma being reliable for Germans? It is the computational power. So the introduction of computers made it able to break Enigma. We are also using crypto systems nowadays called RSA. Now, what makes RSA reliable for us? It is the large prime numbers. So let's talk about prime numbers. In today's presentation, first I'll be talking about prime numbers and existing algorithms. Then I will introduce a new algorithm, I'm calling it geometric algorithm, then how I parallelize it. After that, I'll talk about how I implemented and how did it perform, how I analyze it. So first, prime numbers. It is a natural number greater than 1 and it is only divisible by 1 in itself. If you find a number that can be divisible by something else, that is called composite numbers. It is an important field of study in number theory and it has been studied since ancient era. It has been well known, but it's still a difficult problem until nowadays. Because the distribution of prime numbers is not even. And that's why we are using it to back up in RSA, because it is a difficult problem. If there's a mathematician who makes prime numbers an easy problem, then we have to come up with a new crypto systems. We cannot use RSA anymore. So let's talk about some algorithms for finding prime numbers. The oldest algorithm was found in Greece by Eratosthenes and it's called the Sieve of Eratosthenes. It is found in 300 BC. Next, there was an Indian mathematician Sundaram who invented the Sieve of Sundaram in 1934. Then the most recent one is by American mathematician Atkin, who invented Sieve of Atkin in 2003. So that's relatively new in the history of mathematics. It is an emerging technology. And all of them have a complexity of big O of n log n. So here's an example of Sieve of Eratosthenes, how it works. So let's say I want to find prime numbers up to 50. So I will make a table up to 50 and I do not include 1 because 1 is neither prime nor composite. Then first I will mark the least number, which in this case it's 2. Then I'll remove all the multiples of 2. The next number is 3, so I'll mark 3 and remove all the multiples of 3. The next number is not 4 because 4 is already removed, so I'll mark 5, remove all the multiples of 5. Mark 7, remove the multiples of 7, and so on and so forth. If I repeat this process, I will get all the prime numbers less than 50. And this is the sieve of Eratosthenes. Now, my algorithm has totally different approach. How I came up. I start with the Pythagorean Theorem. So, when you look at the smallest right triangle in this slide, you'll see that there are 1 and 2. I have integer sides. And the hypotenuse of this right triangle is 1 squared plus 2 squared, which is 5, and I take a square root, so it's a square root of 5. Similarly, if I have sides with 2 and 3, the hypotenuse of this right triangle will be square root of 13. And if I have 1 and 4, the hypotenuse will be square root of 17. Then I realize 5, 13, 17, those are all prime numbers. So maybe I can use Pythagorean theorem for finding prime numbers. So there are 3 kinds of prime numbers. There's even prime, which only consists of 2, and there are 2 kinds of odd primes, either 4n plus 1 or 4n minus 1. The 4n plus 1 are numbers like 5, 13, 17. 4n minus 1 are like 3, 7, 11. The geometric algorithm will only focus on the 4n plus 1 primes, which can generate all the prime candidates, which includes all the 4n plus 1 primes, and after I include it, I'll exclude all the composites. The benefit of using geometric algorithm is that I'll have less prime candidates than other algorithms. For example, in Sieve of Eratosthenes, I had to use 50 numbers, actually 49 numbers, for all primes less than 50. For geometric algorithm, I'll only have to compose 7 right triangles for prime numbers less than 50. So that's very efficient. Now let's talk about parallel computing. I'll ask a question to you. If boiling 1 egg takes 4 minutes, how long does it take to boil 6 eggs? I can think of 2 possible answers for this problem. If you answer 24 minutes, that's sequential answer. You're boiling 1 by 1. If you answered 4 minutes, you're using parallel answer. You're boiling all eggs at the same time. And that's the idea of parallel computing. And here are some technical terms. Thread means smallest sequence of instructions. In this case, it's eggs. And load balancing principle means all eggs have to be almost the same size as much as possible. If you boil small eggs and big eggs at the same time, then it will take longer. So how do I apply parallel computing to my algorithm? So here's the diagram. For sequential program, it generates all prime candidates, then it sieves to get all primes. For parallel program, each threads are being assigned to generate prime candidates all at the same time, then each threads are assigned to sieve to get primes all at the same time. Now let me explain that there are 2 processes for this part. The generation of prime candidates is easy to parallelize, whereas the sieving part is hard to parallelize. Why? Because each thread has to access all prime candidates in order to sieve, and it will incur inefficient memory allocation. The geometric algorithm is focused on generation of prime candidates, which means I can exploit the power of parallelization, maximizing its utility, while I'll have less prime candidates to sieve, so I'll have less burden. So here's how I implemented. The problem size is from 2 to the 20th up to 2 to the 28th. I didn't have to use those numbers, but it's a very useful number in computer science. We all love powers of 2. Then I used the parallelization method, p-threads. The number of threads I chose is 8, 16, and 32, which is again powers of 2. The hardware is TACC Stampede 2, which is in University of Texas, and thankfully, we, the students of MSU, have access to TACC. It has 48 cores, 98 hardware threads, and we have hyper-threading. We have the software Visual Studio, WinSCP, PuTTY, Atom. And here's the performance. First, I compare sequential performance of geometric algorithm with other algorithms. At 2 to the 20th, geometric algorithm was the fastest among all the algorithms, and it was the fastest up to the 2 to the 26th. But at 2 to the 28th, geometric algorithm is getting slower than other algorithm for somehow. When I graph them, it will look like this. This is a logarithmic scale, and there's only a very slight difference. So geometric algorithm is running faster than other algorithms but it's getting slightly above other algorithms at larger problem size. Next, here's the parallel performance, comparing the sequential part with 8 threads, 16 threads, and 32 threads. So in each parallel performance, it's getting faster and faster at any problem size. Actually, when I graph them, the gap between the sequential program and the parallel program is getting larger and larger, which means as I run in parallel, it's getting more efficient as the problem size grows. So here's the issues and solutions. First, in order to understand the geometric algorithm, you have to understand the mathematics. Then, since my concern is about time, which runs faster, so I have to use compiled languages like C or C++. I cannot use Python because Python is slow. Finally, the implementation matters, so I have to watch the concepts like memory allocation, using primitive data types, and load balancing principle. Here's the conclusion. Geometric algorithm is conditionally faster than other algorithms under certain problem size, not always. Geometric algorithm is easy to parallelize than other algorithms, and once I parallelize, it has very good parallel performance. And here are the references. Thank you for watching my presentation.